We are now going to use Gauss-Jordan elimination to help us solve problems. And this is similar to Gaussian elimination, but instead of going to row echelon form, we actually take our matrix all the way to reduced row echelon form. So instead of using substitution to finish solving the problem, we just keep using row operations. And so what we're looking at is the system 2x minus 3y minus 2z equals 0, x plus y minus 2z equals 7, and 3x minus 5y minus 5z equals 3. And what we're going to do is we're going to first convert to a matrix. So 2 minus 3 minus 2, 0. 1, 1 minus 2, 7. 3 minus 5 minus 5, 3. From here, we're going to swap rows 1 and 2 so that this 1 goes there. Since we already have a 1, let's take advantage of it. So 1, 1 minus 2, 7. 2 minus 3 minus 2, 0. And 3 minus 5 minus 5, 3. So now we need to zero out what's underneath that leading 1. And that gives us row 2 minus 2 row 1 gets stored in row 2. And row 3 minus 3 row 1 gets stored in row 3. And again, I'm not using these 2 and 3 because of the rows. I'm using it because of the number in the front of the row. So that's going to give me a minus 2, a 4, and a minus 14, and a minus 3, a minus 3, 6, and minus 21. Add those together. So our top row is unchanged. Minus 2 plus 2 is 0. Minus 2 minus 3 is minus 5. 4 minus 2 is 2. And minus 14 and 0 is minus 14. Third row, minus 3 and 3 is 0. Minus 3 and minus 5 is minus 8. 6 and minus 5 is 1. And minus 21 and 3 is minus 18. Well, here's the bad news now. Neither of these is a 1. And none of these are multiple, so I can't just divide without creating fractions. So what I'm going to do is I'm going to take a variant on our rule, and I'm going to take, in this case, I'm going to take 3 times row 2. I'm going to subtract from that 2 times row 3, and we'll store that in row 2. So I'm making an additional change of changing this one by just enough. And so 3 times row 2, I'm going to write this out, is 0, minus 15, 6, and minus 42. And you'll see why here in a second I'm doing the minus 2 row 3. Minus 2 times minus 18 is positive 16, and look at those numbers very carefully. That gives me a minus 2 and a positive 36. So now when I add these together, I'm going to get a 0, 1, 4, minus 6. And that's the row. That's now row 2. So 0, 1, 4, minus 6, and then 0, minus 8, 1, minus 18. Well, we ran out of room on that page, so I'm just going to scroll over to here, give myself room on the next page. Now what we need to do is make this a 0, so we're going to take row 3 and add 8 times row 2, storing that in row 3. So it's going to be an 8, a 32, and a minus 48. We add those together. We get 1, 1, minus 2, 7, 0, 1, 4, minus 6, 0, 0, 33, minus 66. Well, now it's real easy to get a 1 there. We just need to divide. So row 3 times 1 over 33, and we're going to store that in row 3. 1, 1, minus 2, 7, 0, 1, 4, minus 6, 0, 0, 1, minus 2. And if this were Gaussian, the Gaussian stops here. But then Jordan came along and said, hey, why don't we just keep going? What if we go to reduced row echelon form? So now that this is a 1, let's put zeros above it. So let's put a 0 here and a 0 here. Well, this says that we're going to take row 1 and add 2 times row 3 and store that in row 1. And row 2 minus 4 times row 3 and store that in row 2. So that's going to give me a 0, 0, 2, minus 4, and a 0, 0, minus 4, positive 8. So now we add those together. The first columns don't change because these were zeros. The last row doesn't change because we didn't do anything to it. But minus 4 plus 4 is 0, and 8 minus 6 is 2. Minus 2 minus 2 is 0, and minus 4 plus 7 is 3. Let's do the same thing now with this. We've got a 1 here, so let's put a 0 here. So we're going to get row 1 minus row 2 and store that in row 1. And that's going to give us a minus 1, a 0, and a minus 2. And you'll notice we get 1, 0, 0, 1, 0, 1, 0, 2, and 0, 0, 1, minus 2. Well, this says if I translate this back to a system of equations, we get x equals 1, y equals 2, and z equals minus 2, or the point 1, 2, minus 2. And so I get my answer actually from my augmented portion of my matrix. And that's how we use Gauss-Jordan elimination. Finish the Gaussian first, and then just do the same thing going back up to zero out and get it in reduced row echelon form, and then you can read your answer directly from the matrix.